Hi, you probably heard about calculus before, and you probably think that calculus is a very hard topic. But in reality, if I'm being quite frank, calculus isn't the hardest topic of math that I've learned. Of course, when calculus becomes very, very, very complex, at university level maths, yes, sure, calculus can get very hard. But in IB at least, calculus doesn't get too advanced to the point where it's unmanageable, and it's actually not as hard as it's not any more difficult than other topics. So I'm going to introduce to you the idea behind calculus and talk to you about what calculus studies basically in this video and in this video series. So first of all, calculus is divided up into two general branches called differential calculus and integral calculus. Today we're going to be talking about differential calculus, and this is the first topic that you cover in IB Math AHL if you learn calculus. So what exactly is differential calculus? Well, differential calculus by definition is the study of instantaneous rates of change. If that makes sense to you, great, you can move on. But if it doesn't, let's break it down a bit. So when we talk about rates of change, it's basically referring to how much one variable changes in respect to another variable. So when x is changing by 1, how much is y changing by 2, right? And traditionally in these type of relationships, these are linear functions, by the way. These are when you graph these points, you'll get something. You'll get a straight line, basically. Not exactly like this. It does, that this relationship won't pass through the origin, but traditionally, when we talked about rates of change so far up to this point in math, we always refer to it as the gradient of the function. And so you would take any point, any y value, for the same x value, and then subtract and just basically see the change in y over the change in x, and that's how you would get the gradient or the rate of change. And this would equal, in this case, say 8 minus 6 over 2 minus 1 would be 2. That's what rates of change is, basically. It's how much a certain variable changes over a certain change in another variable. And this itself is quite simple for now, and when we add the word instantaneous, this is when differential calculus really takes place. Differential calculus deals with instantaneous rates of change, so it doesn't talk about changes over a certain period of time or over a large gap, basically. It talks about what the rate of change is at that specific point. So let me explain to you with a graph. Okay, so here we have a graph on the right side of temperature to time, and it's basically showing what the temperature level is at a certain point in time. So for example, at 2 minutes, the temperature is at 20 degrees Celsius, and we can see that it's increasing. And so there are two different types of rates of change, and the ones that we dealt with so far are average rates of change, where we take, for example, we take 1 point on the graph and another point on the graph and see how much it changed, how much one variable changed while another variable was changing. So for this case, an average rate of change in this graph, the average rate of change of temperature from 2 minutes to 6 minutes would be the change in temperature over the change in time, which is 4. And so that would give you 5 over 2 as the average rate of change. But what if we wanted to find the exact rate of change at this point or at this point? Because it will be completely different. The average rate of change at 2 minutes, we can see that it's increasing much faster than it is at 8 minutes. And so how do we really say, and how do we really predict the instantaneous rate of change, the rate of change at a given point in time, not over a certain interval of time, but at a specific point of time? That's what differential calculus deals with. And so the instantaneous rate of change would equal to, say, if we want to find the instantaneous rate of change at 8 minutes at this given point in time, not over a range of 0 to 8, but at this specific time, we would have to draw what's called a tangent line. And a tangent line, by definition, is a line that touches a curve at exactly one point on that curve. That's what a tangent line is, and the instantaneous rate of change would be the gradient of the tangent line drawn at the exact point in time. We'll be talking about something like this, instead of trying to find what this change is, because that would be the average rate of change. So those are the ways it kind of differs. So when we talk about differential calculus in more technical terms, basically it deals with derivatives of functions. So when in differential calculus, the process in which you take to get from a function to another function that talks about the rate of change of that function, you have to do what's called deriving, and then you would get the derivative of a function. So this would be the original function, and this would be the derivative of that function, denoted by this little line here. So let's say we have a function 2x squared plus 3x plus 5. And this function, let's say, gives you the, let's put minus here just for realisticness, I guess. This function gives you the position of a projectile over a certain period of time, where x is equal to time. That's not really necessary for what I'm trying to say, but if you want to know any rate of change at an instantaneous point in time, you would have to do what's called deriving, and you would derive this function to get a derivative of this function. And so if you do that, you don't know how to do it yet, but it would be 4x plus 3, and that would be the function to plug in your time value to find the instantaneous rate of change. So let's use an example here. If x is equal to, say, 5 seconds, after 5 seconds of that projectile going, where is the position of that projectile? If we plug in 5 to this fx, to this function, we would get the position of the projectile. So you would be able to get the position as minus 30, wherever that's relative to. And so this is the position value, but you're asked to find the rate of change of when the projectile is at this time. So then what you would do is take that same x value and plug it into the derivative of the original function. And so if we do that, if we plug in 5, we'll get minus 4 would equal minus 17. And there you go. This would be the rate of change at which the projectile's position is changing at this time. And from this, we can tell a derivative of a certain function is going to be the function that gives you the value of the gradient of the tangent that we discussed in the previous slide. So this would be the gradient tangent line. And this comes in really handy when you're asked to find specifically the equation of the tangent line at this point of this certain function. A lot of technical terms there, but if you really understand this, if you take your time to absorb this and understand this, differential calculus has nothing else to it. This is literally it. It's all about deriving a certain function, a given function, to find the rate of change of any value in that function. So another thing I want to note is that there are many different ways to write the derivative of a function. The most common notation would be the f of x with, or the function with an asterisk. Wait, is that oh no, with an apostrophe, sorry. I've been saying an asterisk, it's an apostrophe, or whatever you want to interpret it as. There's going to be a line in between f and x. So that's the most common notation. It can also be written as dy, dx, and this would mean the exact same as this. It's talking about the derivative of a certain function that it is written to y. And the least common way of writing a derivative is y apostrophe. So when you have a function, say y is equal to 2x plus 3, the derivative could be written as y prime is equal to 2. And this, honestly, stay away from this. Is some people will write it in this way, and it might be worth it to realize, but the prime of a certain value is written or is used in many different ways in mathematics, so it might be a bit confusing if you use this consistently for derivatives and derivatives only, because it will confuse you later on. Try and stay away from this notation. This is the correct way to write it, and dy dx is kind of like a synonymous way. It's the exact same thing of writing this. But yeah, that's really all there is to it, to differential calculus. It's basically the study of instantaneous rates of change, and the instantaneous rates of change are different from average rates of change because average rates of change happen over a longer period of time. Instantaneous rates of change, as the name suggests, is the rate of change of that certain thing in a specific point in time, or a specific point in that change in variable. So if you understand to that point, you're fully ready to move on to learn the different rules of differential calculus. So thanks for watching. I hope that helped. I make videos on math, AHL, physics HL, and chemistry SL. So if you have any topics that you want me to cover, please leave them in the comments below. Otherwise, thank you for watching. I'll see you in the next video.